Welcome students. Today we will discuss about the application of genetic algorithm to optimize this fitness function. The fitness function f of x is given as absolute value of x plus cos of x, and here you need to find the optimum value between minus 20 to plus 20. So let us see how it is possible. So let us see the syntax here. The syntax for genetic algorithm is S is equal to RBGA. This is the name of the function, and it is already available in our this library function. This library genetic algorithm GENALG. In this library we are having the genetic algorithm. So you need to understand this genetic algorithm. It is a not binary version. It is a real value version of genetic algorithm. That means you can represent feature in the form of real values. So that's it. The first argument is a lower vector consisting of lower range of values of all variables, and upper is vector consists of higher range of all variables, and the third argument is population size. That means how many solutions in the population, and the fourth argument is iterations. So how many number of iterations the algorithm has to execute, and the fifth argument is the function, monitoring function. So you need to understand that monitoring function generally it is used to calculate statistics or plot the curves. This monitoring function is called after every generation of a population. Okay, and finally, and the 3, 4, 5, 6th argument is our fitness function or evaluation function. In our case, you can see this is the function. So this is the function we have to implement. We have to pass this to the argument. So after understanding this, we will go to the next step. So after executing this function, genetic algorithm function, it will throw you the output object. See here, the output object is a list and it contains several elements. So first element is population. With this first element you can extract the last population. That means all the solutions in the last population, and there is another element in the output object S is evaluations. So the fitness value of all members in the last population will be stored in this evaluations, and then $best. So since S is a list, so you have to use dollar symbol to extract all the element values. So best means it will give you the best value per generation. Okay, by default you have to understand this is RBGA. This genetic algorithm, it is used to calculate the minimization problems. It will perform minimization problems. Okay, minimization problems. So if you give any fitness function or evaluation function in this position, in this argument, it will calculate the minimization. It will perform minimization. And finally the mean, and another element in the output object is the mean. You can extract the mean with the help of this parameter. So once understood this, here in genetic algorithm package you are also having the plotting functions, plot.rbga, and summarizing the results also. So let us see, first we will implement this function. So let us define, after understanding this function, we will define all the arguments as per our problem. First one is lower and upper vector. This you need not define directly, you can pass it. In our case it is a scalar value. It is a single dimension and the range is minus 20 to plus 20. So dimension is d is 1. So let us first define the evaluation function. So it is a simple, first load the genetic algorithm and then fitness function you define is, you pass it, So we all know how to do it, and then define how many number of iterations. Next step is maximum number of iterations, and k is equal to 30 means here I already told you, for simplicity we are going to plot. We already told you in monitoring functions we are going to call the monitoring function for every prescribed generation. So if k is equal to 30, we will call for every monitoring function. So 30, you can change this value also, and I is equal to 1, it represents initial generation, and d is equal to 1, it represents the dimension. For this problem, d is equal to 1. Now let us define the monitoring function. Generally this function is called after generation of each population. For first population, you will plot the population, you will plot the population of solutions, and here you can see the different arguments are there. Some are you can see obj, this is the output object, and you are calling the population, and x-axis is in between 0 to 6. See, this you can change depending upon the problem. I tried, and finally I fixed it at 0.6 for this problem, so that you will curve, your plotting will look nice. And this is the range of y-axis, and then the labeling for x-axis and labeling for y-axis. Next you have to understand is what is the type you have to plot, and then 16 represents the point, and for each population there should be some differentiation. Here we have made the differentiation with the help of color. So for each population different shades of gray color will be applied. So for first population, for remaining population, this code will be executed. This code is simple. The same points will be appended to the existing plot. So here this monitoring function, it is called for every population, and for every population we will execute, we will plot the points, population points on the graph. Okay. Finally, after defining monitoring function, this is a monitoring function. This is here we are using for plotting purpose, and after implementing the fitness function of our thing, we will call the genetic algorithm. This is how we will call the genetic algorithm. Genetic algorithm. So we will pass the lower vector, will pass as a directly. So here we are using a repetitive function, and then here d is equal to 1, we have already defined. And the upper vector, so you can see this is the maximum value, and then we have to define the third argument as population size, how many solutions in each population. So, and then how many iterations. So here in this application we have taken 100 iterations. So you have to try 100, 500, 1000 like this. You define you pass the monitoring function in this argument, and finally our fitness function, which we have defined here. And after that you can execute the algorithm. It will throw you the output object. Once you got the output object, now you have to print the results from the object. So $.evaluation which dot min, that means it will give you the index location. With that index you can calculate the best population. So I already told you the output S object consists of the population element and evaluation. So since we got the index, minimum index, you can, with the help of minimum index, you can print the population and its corresponding fitness value. Okay. So that is how we are going to do. So this is not necessary. Now let us execute one by one. So you can see the run button here. So you can see my output in the bottom window. So you can see this at the right hand side. You can see I think it is visible for you. You can save the image. You can see in the right hand side the panel, you are getting the plotting. So you can save this also. You can save this plot, and you can see this different colors represent different population. After executing, you can print the results also. Next statement. Now this statement, you can see this at this position, this is the best value, because at this x value you are getting the minimum fitness value. Okay, so this is the optimum value we want to tell. So if you want to find out this curve also, it is also possible. So when you execute the plot of S object, it will give you something like this. So you can see this x-axis is the generation, that means iteration. So here we are executing for 100 iterations. For each iteration, see the fitness value how it is decreasing. So you can see the curve also. You can save this curve, save images. Okay, or you can save in your favorite directory, say for example desktop. The file name is rplot, or you can put any name, gen plot, save. So we have already saved it. Let us see. Now you can see my screen. So in this way you can execute this program and plot. You can get the plot of fitness value with respect to different iterations. Thank you, students.